Alright, welcome back everybody. We're going to attempt recording with my personal computer and see how things go. This is where we are right now. Types of forces. So if we go to the content, we did Newton's law of motion last week. And now we can go with forces. And where should we stop? A free body diagram. So here. Okay, so just this. So there's 19 pages. But is it going to take 2 hours again? I don't know. When we have a conversation about things that we care about and are complex, right? This is 11th grade, 12th grade. Things are getting complex. And it's normal, I think, to have to discuss about them more. Because they're more like precise. Every time you go in education, it's more precise and precise and precise. And it needs more time to assimilate and grasp, etc. Let's go. Types of forces. So let's say we're done with this week. And do you hear this now?
Module 2, Dynamics. Types of forces.
Yeah.
Forces can be classified into two categories: contact forces and action at a distance forces.
What? Okay, these are the pictures. They're a little like distorted, right? This should be like in here. Okay. So contact forces will be when you physically push something else, right? Action at a distance might be magnets, right? So magnets will push or pull each other. So these are forces because they cause movement, and as soon as they accelerate things. So there's contact force and action at a distance. Again, not something that I'm familiar with, because a force is a force. If you know it's causing a force, whatever the source it is, it's a force. And it's accelerating something. Alright. So a gravitational force is action at a distance, because anything feels the force of attraction. We're going to rip the whole thing.
Dynamics. Action at a distance forces. Gravitational force. Let's start by looking at an action at a distance force, gravitational force. The gravitational force exerted on an object by the Earth, or another planet, is known as its weight. Weight is calculated by multiplying the mass of the object by the acceleration due to gravity for the planet on which it is located. As you learned in the previous module, the acceleration due to gravity on Earth is represented by the symbol g and is equal to 9.80 ms2, or 9.81 ms2. The formula for calculating weight is
just such a simple lesson.
Fw equals mg. In this formula, Fw is the weight, n meters is the mass of the object, kg, and g is the acceleration due to gravity. Instead of writing Fw for weight, you can use the symbol W and write the formula as W equals mg.
Okay.
Tip. Remember, G is always positive. The force of gravity can be represented in a variety of ways.
Positive. Why is that?
You may also see it represented as Fg.
Alright. So a lot of few things that I'm not sure about. So Fw for weight, we get that. I don't like using W in my physics because that's work. W is normally used for work. Fg makes a lot more sense. The force caused by gravity. So that I prefer this type of language. So force caused by what? So if you had a force caused by Charles, a force caused by Michel, a force caused by John, you would write C, FC, FM, or FG, right? For Charles, John, Michel. So it's easy to identify that way. So W I don't like at all. G positive means that your mass is always positive. So if your G is positive, it ensures the product is positive and that the force is positive. This is useful if you want to compare, like, you say you have a 40 Newton force versus a 20 Newton force, right? So if they're both positive forces, they kind of add up. But if you say one is versus the other, they go one against the other, then you are subtracting them at some point. So again, G always positive. I don't see the necessary or the purpose for that. I'd rather use a minus G. Put some directions. Let's take a moment to clarify the difference between weight and mass. So weight is newtons. Mass is kilograms. So when you hop on the scale, it measures the force that you push on a plate, and by knowing the amount of force in Newton, it does a simple calculation, or it uses a spring to convert the force into movement and then show you the appropriate kilogram. So that's why when you go on a scale, you only see the reading of kilograms, but what's happening is that it's measuring a force, converting it into movement for the read, and the read is proportional to your mass. Well, a lot of things are going on in a scale, but the weight is in newtons, the mass is in kilograms. Next. Let me try and plug this. I don't know how much battery I have. So Fg will be equal to mg. It's lagging. I don't know why it's lagging. This is a small g, smaller than this, just as a little note for F, right? Yep. So here we have the weight. We want to know the weight of something. You put a 20 kilogram mass, multiply it with the gravity or the acceleration it's exerted on, and get the result of weight. The weight is a force, a downward direction. So basically this has a force by being on Earth, attracted to Earth, equal to that much. And they also come back here on the negative aspect, because it's going down. In our problems, it's always going down, so it's always negative. So you should just put your negative here, because it's accelerating it downwards. Next. Solving problems using the weight formula. Okay. I'd like to know where the lag comes from. I've been trying to pinpoint it. One moment. Okay. An object has a weight of so we do examples. Example 1. An object has a weight of 500. Wow, I'm lagging. It could be because it doesn't have enough energy. Okay, one moment. What do we say about technology? It's nice, it's wonderful when it works well. It's wonderful when it works well. I think that fixed it. So it's the energy inside the tablet that was too low when it communicates wirelessly. Interesting. An object has mass 500 Newton on the surface of Earth. What is the mass? Mass is unknown, and the acceleration on Earth is g, minus 9.8 meter per second square. So basically, we would write Fg equals mg. Again, my g here is not like small enough. I want to give you an example. Fg, like this, is equal to m times g. And I want to move things around because I'm a good boy. I'll move things around. So g is going to go on the other side. How? We divide by g. Divide by g. These cancel out. M is equal to Fg divided by g. .500 Newton divided by minus 9.8 meter per second square. It's too big of a scale. Oh, no. M equal. So, is there a calculator? Where's my calculator when I need it? Really odd. .51 .02 kilogram. Kilogram. So my answer is more precise. I recommend always 2 or 3 for kilograms and 1 digit only for degrees. An astronaut whose mass is 95 kilos lands on asteroids. Find the weight is 35. I'll try this. Example 2. We have an astronaut whose mass is 95 kilograms, lands on an asteroid. So he finds that his weight, or the force by the gravity of the asteroid, is only 35 Newton. What's the acceleration of gravity on this asteroid? So he's not on Earth, but on an asteroid. So the acceleration is not going to be the same. Now, if we imagine that he's on top of the asteroid, well, like here, then the force is pulling him down. So this force would be a negative force, because it's pulling him down. But if he's on the other side of the asteroid, what is going on? If he's on the other side of the asteroid, it's pulling up. So that's why they don't want to mess with the direction. But we will. So, interrogation. Force is mg or ma. Did they say what the acceleration is? Yeah, we'll put an a. Yeah. Doesn't matter. So a will be equal to fg over m. So what I did here is I did what I asked you to do on paper in my head, and I wrote the result. It makes my paper a lot less scramble. Like if I move things around like that, it's harder to read. Whereas this is true from here to here, that's true, and it's easier to read. And we can clearly see that I've isolated A. And it was only one step, so that's why it's easy to read. And then A would be minus 35 over 95, calculator, (35 by 95). Whoa. Minus 0.368 watt meter per second square. .37. Yeah. Good. We're good. Elephant weighs 3,600, 431. I think it's going to be a short module, so we're gonna do some examples, because some examples are going to be interesting. No more. Okay. Example 3. An elephant weighs 3,431 Newton on Pluto, and they give you the acceleration of Pluto, which is 0.062 times the gravity on Earth, minus 9.81 meter per second square. So Pluto is that much of this. And if I say 1/4 of something, or if I say 1/3 of something, the of is a multiplication. So 0.062 of this will always be a multiplication, right? If I would say it's 1 time of, then it would be 1 time that. If it's 2 times of, it would be 2 times that. It's that much of this. And what's the mass of the elephant? So it's an easy one. I was expecting them to like tell me what the mass is and then find the force on another planet after that, which we could do. So mass is unknown. And we can simply write mass is Fg divided by G, or A. You could start like that, I don't mind. You just need to not mess it up. So Fg divided by the acceleration. This, by the way, should be written down before we get into that. It doesn't matter, but let's write it down. What's 0.062 of gravity? You'll notice I never put minuses. Oh. I never put minuses in my calculator. I do that in my head. I take the numbers. And then here's a minus. I put a minus. And I put that number. 822 meter per second square. Why do I keep so many digits? We're probably going to end up with 2 or 3 digits. These will affect the last one. Yeah, you want to keep a lot of digits before you, like 4 to 5 digits is not bad at all if you want to end up with 2 or 3 digits, because they're going to affect your numbers up to when you decide to cut it off at the end. Yeah, that makes sense. Okay. What's the result? If you take, there's a cool functions on the calculator. I don't see it here. Inverse? No. Answer? No. 3431 divided by 0.60822. Okay, so the minus stays. Do you see how that makes no sense right there? Holy. Sorry. Gonna have to fix that. Do you see how you cannot have a minus as your mass here? So what happened? What did we do? Right, so the acceleration was negative. This is our elephant. On a planet. It's accelerated downwards because there is a force that is also downwards. So the force, if I want the acceleration to have a minus here, I should also put a minus at the force, which we will. And now this has a minus. So the force is negative because the acceleration is negative. The two negatives cancel out to make a positive force, positive mass, which makes sense. So you should always have a positive mass. Kilograms. Sorry. Limits. We'll get it. We'll get it. Don't worry. Next slide, please. Applied forces. Next several screen, 5 contact forces. All right.
Module 2, Dynamics. Contact forces, applied force. The next several screens will introduce you to 5 contact forces, applied, spring, tension, normal and frictional. Let's start with applied force. An applied force is a push or pull that is applied on an object by another object or a person. For example, the man in the image is pushing the wheelbarrow by applying a force. The symbol Fa is used to identify applied forces. Remember, forces act in pairs. Whenever there is an applied force on an object, the object exerts a force that is equal in magnitude and opposite in direction to the applied force.
You catch that? What did it say? So an applied force is a push or a pull, and it's applied by another person. I'll take the push. It's push or pull, which every force does, but it's just applied by another object or a person. So we'll take that definition. Oh my. So is a push or a pull, but I don't see why they write that. An applied force is applied on an object, is applied by another object or a person. Force act in pair. So when I push, this pushes back against me. And did we have a note on how to call it? They call it FA for applied. Okay. Okay. Why is it so much? So FA, Pepe Love, FA is MA, and no G's here because, again, it's not caused by gravity. It's us causing this acceleration. So something slammed it, pushed it, pull it, and it's being accelerated for real. And so most of the time when we push or pull something, we are trying to accelerate it. But it has nothing to do with gravity and none of that. It's also mostly on the x-axis. So we could call this Fx, but Fx is mostly maintained for the sum of Fx. Well, Fa seems good. Or just F is fine. Spring forces. The spring will either stretch or compress.
When a force is applied to a spring, the spring will either stretch or compress.
What?
When a force is applied to a spring, the spring will either stretch or compress.
Oh, that's odd. Let's reload it. Really odd.
Module 2, Dynamics. Contact forces, spring force. When a force is applied to a spring, the spring will either stretch or compress. The counteractive force required for the spring to return to its original state is called the restoring force. Spring force also involves a spring constant, which indicates the stiffness of the spring.
So this is kind of a new formula because it's a new phenomenon. Let's put this spring here on the wall. So imagine we have a spring and it's at rest, right? So it's not moving. The spring can be compressed. Okay, so you can see here the spring. It could become compressed, right? Or it could be pulled. So we're going to start with pulling. So if we pull the spring up to here, this is at rest, so nothing was touching it. So it was just a normal spring. When it's on that position, there is no force applied by the spring. Like if you compress it, the spring pushes back on this side. So when you push it on this way, the spring reacts on the opposite way. And if you would be to pull it like that, you pull it like this, but the spring pushes back or pulls back on the other side. Again, so that's why the force always has a minus. It's always going opposite. Not necessarily because it's opposite to my force, but it's mostly because it's opposite to this. This is the distance, x, that it traveled. So between the resting point, which we will call 0, to the new position, which could be 1 meter or 1 centimeter or whatever, this is the x here. So if the x becomes positive 1, like this, because it's going in the positive axis, and the constant is always a positive force, then the result should be a positive force. Plus times plus is positive. But if it went in the positive direction, it is pulling back. It's pulling in a negative way. So that's why we put a negative in front of it to make a negative force. So that's where the negative comes from. It's just to use it as a negative, because if you travel in the positive distance, you result in negative force. Like the spring is pulling you back. When you pull it forward, it's pulling you back. And if you would go to a negative distance, like -1, this is 0, remember. This is neutral. If you pull it by -1 meter in the x direction, then it has a positive force. It's also easy to figure out what this is, because if this is a Newton, and this is a meter, then this is Newton divided by meter, right? So that way the meters cancel out and newtons are left. So basically, K is a measure of the spring. In Newton per meter. So in other words, if I tell you I have a spring that has a spring constant of 1 Newton per meter, it means you need 1 Newton to stretch it by a meter. And if you want a stiffer ring, or a spring, you would have a bigger number. So if it takes 3 newtons to stretch it by a meter, or maybe it takes 30 newtons to stretch it by a meter, so you can see the stiffness of the spring. If it's a very light spring, then 0.3 newton to stretch it on a meter will be much easier. So this is the idea for the spring. And it's really special. Like, if you increase the distance by 2 times, then you increase the force by 2 times. It's directly proportional. Okay. So basically, you would take a spring, find the right distance, it's proportional to the force, and you could match that in your system. Continue. Depending on the spring material. This is a fun part. We're not getting into that. But I like how you can take materials and use an equation to figure out these things. And x is the amount in meters. So is this just better than my drawing? Cool. Contact forces. Tension. All right.
Module 2, Dynamics. Contact forces, tension. Tension is the force that an object, such as a rope, rubber band or spring, transmits when it is stretched. The image shows an example of an object hanging from a rope. As the rope holds up the object, tension is created throughout the rope and then acts on the object. The weight of the object stretches the rope just enough so that the rope applies an upward tension force on the object that is equal in magnitude to the object's weight. A tension force is always directed along a rope, or similar object, and is always a pull. In the image, the vector is pointing away from the object because this is the direction that the tension force is acting, pulling, on the object. A vector showing the force exerted on the ceiling would be pointing down. The symbol T or Ft is used to identify tension forces. When you solve problems involving tension, ignore the weight of the rope itself. Video. Click here to view a video from Flipping Physics that shows another example of tension. Pulleys.
Flipping Physics.
A pulley can be used to change the direction of a tension force without changing its magnitude. As shown in the image below, the rope must have tension in order to pull the wagon. By adding a pulley to the rope, the direction of tension after the pulley is changed. Note that the pulley itself does not create a force.
Okay, so we're getting into the more complex things. The tension, if the object is not moving, yet it has two forces on it, like this object has a force, which is weight, but it's not moving. So if it's not moving, and it's not accelerating, that means another force is going against it. And if they are equal, then there is no acceleration, and thus no movement. So there, since it's not moving, and it's on Earth, there is a tension. Tensions are always in material holding things. So a string. Can I copy and paste that? Cool. Okay. So in this case, the tension is a force, and it's opposite but equal to Fg, or W, or the weight, which I will call Fg. Call this Fg. Tension. Cool. And it will be caused by, or equal to, minus, because the minus from here, mg. So this is m. And g simply applies. What do you want to show me?
Good morning. Today we're going to learn about the force of tension.
All right.
Hey guys.
Hey, Bo.
Hi, Bo.
Flippin' physics.
The symbol actually stands.
All right. So he's doing what I do here.
String or wire pulled taut by forces. Wire, string, attends to the direction of the tension forces as directed along the rope. We call it just the tension force of the rope. So there are two different forces of tension. Tension force 1 in the rope segment on the left.
A lot of things writing here. So he's holding it, but the rope could be sliding, but he's still holding it. And he feels that tension. And then he feels that tension.
And tension force 2 in the rope segment on the right. All the rules.
And he's not necessarily pulling, like they are pulling. The two people here are pulling.
Tension is a pull, and is
He has to pull if he wants to counter those pulls. Like if he wants to counter some of these pulls, he has to pull too.
Notice the concept of.
Thank you. Pulley can be used to change the direction of the tension force without changing its magnitude. So we'll use pulleys to change the direction of the tension, which will be down instead of straight, but it will not change how the force is applied on this wagon. Right? It's still going to go forward. And they say the pulley does not create a force. It simply changes the direction of it. There's a lot of force on the pulley itself because it's going to break at some point if you use it for 1,000 years, right? All right, normal force. This is a very important one too.
When an object is in contact with a surface, the surface exerts a force on the object that is perpendicular to the surface. This force is called normal force.
Okay.
When an object... Module 2, Dynamics. Contact forces, normal force. When an object is in contact with a surface, the surface exerts a force on the object that is perpendicular to the surface. This force is called normal force. As shown in the image below, the normal force is perpendicular to the surface regardless of how the surface is oriented. The symbols Fn or N are used to represent normal force. Normal force is the force that prevents objects from passing through each other. For example, a person that weighs 500 N exerts a downward force of 500 N on the floor. The person does not fall through the floor because the normal force pushes upward with the same magnitude. When forces are balanced, there is no acceleration.
Right.
Think about this. Consider the book sitting on the desk in the image above. Do the forces of gravity acting on the book...
Oh, making me think. So the force, so the book is not moving, yet experiencing gravity. Same thing as tension. The table is pushing back on the book. And if the table were to be made of paper, then the paper would push back on the book as much as it can and then break. But the table is not made of paper, it's made of wood, it's strong, it can push back. Again, no, unconsciously, it just happens. The normal force is then the opposite of the force of gravity. And it's an important force because every time you're going to have a mass in a system, like this is your mass, M. You always have gravity, right? So Fg. And if it's resting on something, then you always have N or Fn. I prefer N for normal force. Fn is often used for net force. We'll use N, straight N. But N is a force. Like I could have wrote Fn. There's nothing stopping anyone from doing that. It's just we're messing up Fn and n. By convention, everyone understand what n is in a system of force. And in this case, same thing as tension. N is the negative of Fg, which is also caused by minus mg. So huge. This part here is going to be like the first part of our chapter, 1/2 of the chapter. And this part here, inclined, we will get to that hopefully within a few weeks. Is the other half of the chapter. So once we know what happens on flat surfaces, and if I pull something and I pull the other way, that's one type of scenario. But what happens on an inclined surface? So anytime there's an incline, right, instead of being flat, there's a little incline. And if I pull on the book, how is that going to change the motion of the book? And you'll notice how the normal force is at an incline. Okay, we'll put theta here. Theta is actually equal to the incline. It's the same angle. If you do a little math, angle relationships in math with like a 90 degree and a smaller angle and etc., they are equal. So the incline will be used here to work on the force and etc. So first part of the chapter and second part of the chapter. Not always equal to weight. Force was pushing downward on an object. Yeah, so basically the normal force also says if I push down on this book right here with my hands, then it increases the n by the table on the book, right? So if I push it down or if I sit on it, then the normal force also increases. Normal means perpendicular in physics. Yeah, I assume. It's been used like that a lot. Friction. FF. What's good?
Module 2, Dynamics. Contact forces, friction. Friction, FF, is the force that acts between surfaces that are in contact. The force of friction is parallel to the surfaces and opposes their motion. The value of the frictional force depends on the types of surfaces that are in contact, the magnitude of the forces with which the surfaces are pressed together, that is, the normal force. Interestingly, the size of the surface area in contact does not affect the frictional force. For example, the frictional force is the same whether you slide a filing cabinet on its bottom or its side. Although this seems counterintuitive, it is generally true. Video. Click here to view a video from Flipping Physics that explains friction in a little more detail.
So you recognize FA here being the applied force. Now we're also saying when you apply a force on something, there could be resistance, not by the what's the word again? You know when an object doesn't want to move? Not friction, but Newton's second law. Help. first law. What was the word again for first law? Inertia. So this is not inertia. This is not when I'm pressing on something, it's accelerating it. If there would not be inertia, it would probably accelerate faster and change our models. But because there's inertia, an FA accelerates the object. It doesn't give it an instant speed, right? So that doesn't change. But if there is a contact by that object on the ground, then you might think that by pushing this box 10 Newton, you would accelerate it, right? If 10 Newton is equal to MA and the box is 1 kilogram, then you might think you're accelerating it at 10 meter per second, which would be true if the box was in the air or in space. So even if you push 10 Newton, you'll notice you're not accelerating by 10 meter per second. Why? Because there is a friction force, FF, that is reducing. So the force might be 10 Newton, positive, and you want to accelerate the box by 10 meter per second, but you have a friction of, say, 3 Newton worth of friction. And so the result of this would be 7 Newton, which would then cause your acceleration once you're done with mass here, 1 kilogram, and the acceleration would be 7 meter per second square, about, or it would be. So that explains why, or how force, friction affects the force. We'll keep that. And we'll bring that down. If I may. I don't know. Thank you. Right, so you get the idea. How do we calculate FF? And it's also interesting how the frictional force depends on the surfaces. So in other words, this skin surface with this skin surface has a friction. But if I were to put the skin surface on the table surface, it has a different friction. And if I put the skin surface on the wall surface, it has a different friction, a different sound also. So the friction has to do with the type of surfaces. And also has to do with the magnitude of the force of the surface that you press on. So there's more friction if I push on the surface more. Same with the table. You don't necessarily move your hand if you put a lot of force on it. Same over there. So the force that you press things on and the type of material will cause that friction force. And the friction force goes against the acceleration force that we're trying to imbue the object with. I don't want to show too much YouTube in my YouTube.
However, if the block is sliding down, it's actually rough and have hills and valleys interact, which increases the force of friction.
For the types of surfaces.
There are means
Mass.
of relating to surface area. Friction will remain the same.
Oh, right. That makes sense. So this...
Or, in this case, the force of friction could be up, the block.
Okay, I'm good. There's a lot of points that we can make. Interesting how it does not depend on the size of the surface area. So it doesn't matter on the surface area itself, even though what we talked about was only surface area. But so the intuition is that surface matters. It does also. The types of surface matter, and also by how much you press on it. But pressing on something has nothing to do with the area, right? These are two different things. And so we're going to take this here and copy that and bring that over here. Now, do you need to remember this? Well, you will in the formulas that you use. So we're not done looking at formulas. When we're done looking at our formula system, then you will integrate all these interesting ideas into the formula system that we use. A lab? I won't grade the lab. I'm not grading any lab. We're going to go take a look here. Yeah, go ahead. Colorado EDU. And you want to use friction. Friction. Yes. Okay, so speed, values, let's put everything. So by pushing it, okay, so there is friction right now from the box because of the weight of the box with the material here. And if you calculate 50 kilogram, so if you want to know what the friction force is, we should be writing it down. F is, do it N, and what? When are they going to introduce that? Oh, I'm good. Two types of friction. Ah, right. Welcome back. Okay, so we can calculate that this poor block, as you can see here, as I'm pushing, the 94, or the friction, does not change. And it has to do with the mass, right? So you can see that 100 kilos will give you 18.8 Newton worth of friction. Based on the material on the ground. But the person, even though it's pushing at 500 here, against the friction force, then the result is 312 Newton, which is the green line. Let's slow it down. And the 312, that is up here, is the result and causing the acceleration, the true acceleration. And if you let it go, then there is friction. This is the only force acting on it, so that's the green is the resulting force, causing the deceleration. until it stops. So as long as there's movement, all right. So here we also see that the force of friction is pushing back on our guy here who's trying to apply it, because the friction is too great to even begin a movement. And the guy's going to push as much as he can until he reaches 188. At 188, the friction will be maximum. And if he goes beyond 188, then he will push further than, well, he's supposed to be pushing more than 188 right now. So why is he not moving? It just so happens that when you push an object, did you ever notice when you push something, sometimes it tips over before it starts moving? Right? Like if you push a filing cabinet, right? So you can push like so get a filing cabinet moving, and you can put your hands on the filing cabinet at the right place, keep pushing it, and it will keep moving, and it won't tumble. But if you stop, or if it stops, and then you try to push it again, it might not move this time, it might topple. Okay, because there's two types of friction forces. The first type is the static force of friction. It needs a little more to start moving. Let's do that again. So I'm at 188. It's not enough. You push a little more, and I want you to notice what's going to happen to the red friction bar once I push a little further. What happens to the red bar? It lowers down to 188. So the static force was broken, and now the 188 would be the not static, but kinetic friction. The first is static friction, is to get it moving, and then the kinetic friction, which will be lower, always lower, to keep it, so when it's moving, right? So one is for not moving, and the other one is when moving. And when it's moving, you'll notice that 188 works, and as long as I push a little more than the kinetic friction, I'm good. I'm 5 Newton over. Right. If I stop, which is 188, so sum of force is 0. This is just enough to keep it going, but he's still pushing. He's pushing 180. If I push a little less than 180, he slows down, and when his movement stops, now his movement stopped, I'm going to need more again to start it. See? So when he's not moving, we're using the static force to decide if he is moving or not, or if it's strong enough to make the object move. And when the object moves, we're going to talk about kinetic friction to know by how much it's slowing down. Okay. So I want to do one more thing before we're done. Let's push this thing fast. Let's release it. So when we release it, you can see that it's pushing back. Now I'm going to pull or slow it down. Notice how fast that happens. Because the friction was, I was helping the friction. Right? Okay. So static friction, Fs, when the objects are at rest. Again, just putting some notes here for you. And kinetic friction is the objects are in motion. So if the object is not moving, we want to know if it's going to be moving or not. And if the object is already moving, then we don't want to stress with the static friction. We just want to talk about the kinetic friction, FK or FF. Yeah. All right. This is a graph of what's going on. As the applied force increases, the frictional force increases. So if you apply the force, you increase the frictional force. Here too, more frictional, more applied, more frictional, more applied, more frictional. Until you reach a point that there is so much applied force that is the very limit of the frictional force, of the static friction, at which point the object moves. When he moves, he doesn't give you that resistance that is due to the static effect of having two objects sitting on top of each other. It's like a glue without being a glue. You know what I mean? This is the static friction. It's like a glue. And if you push hard enough, you'll pass beyond that glue. And this is exactly what it is. It's like a glue effect. When you're using normal words in physics to talk about not normal things, you know you're doing it right. So the glue effect is bypassed, at which point the physics of our world says you don't need that much, you don't receive that much force of friction when the object moves. So that's what we can see afterwards here, this rapid decline, but stability. So even if you apply more force, the frictional force stays the same. Again, applying more force, I'm increasing on that axis, yet on this axis it remains the same value. So we could see that with our box earlier. 188 did not change. Whatever force I was applying to the box, it kept pushing back at 188. Let's read this fast. The graph shows what happened typically when you investigate this type of situation as applied force increases. This was static force. At this point, an object moves in periods after periods in constant speed. Notice that more applied force needed to overcome. These are all words I know. Static force and Newton's law. For example, imagine that the maximum static force used for a book on your desk is 5 Newton. So this means that I can't push the book on my desk unless I push at least 5. You try to push the book with 3, the static frictional force would be 3, and it would not move. However, if you push the book with an applied force that is greater than the force, you get 6 Newton. It would overcome the static of 5. And we would simply say 6 is greater than 5. 6 Newton is greater than 5. And this would be the force of the kinetic static force, which we can calculate. And this here is the FA, which is either given or calculated. So if the FA is bigger than the FS, the object will move and you can move on with your problem. Moving on. There you go. solving problems using the kinetic friction formula. Okay, so so Fs is going to be equal to mu s n. Remember n from earlier? The normal force? It is primordial. So important. So we'll find the static force using a coefficient of force. Is a coefficient. I'll try harder. So mu k is a coefficient that is given to you. And the coefficient has to do with what again? Depends on what? The types of surface and the magnitude of the force, or the normal force, or n. So the normal force, n, and the types of surface. And the types of surface will create a coefficient, mu. We can calculate the coefficient. It has to do with surfaces. So once you know the mu between rubber and wood, or the coefficient between steel, and the coefficient between wood and wood. So you have all of this, and you can find them online if you just write coefficient of kinetic friction. If you're asking yourself, can I put this object, will it move, right? If it's on ice or etc., you can say, Google, give me some coefficients for kinetic friction. Can I have examples? Yeah, here's some examples. Here's more examples. So you can see the static friction and the kinetic friction. It's often given to you in the problems, but you could look it up online. If you have a plastic glass resting on a wooden table, I wouldn't believe we can't find that. Plastic and wood. So the coefficient of between plastic and wood, right? You could look it up here. Soft plastic on dry wood, hard plastic on dry wood, soft rubber. Wow, that's a strong coefficient. I don't think the coefficient goes over 1, so anything close to 1 is very good, very strong. And you could calculate it if you give it an incline until it starts falling. That's one way to calculate the friction coefficient. So basically, Fa, which will be the kinetic force of friction, will be calculated using mu k n. This is a formula that we can put in our toolbox. So a lot of new little formulas today that we can put in our toolbox. Okay, so example, solving problems using kinetic friction formulas. Snowboard has lunch. Let's write down some new formulas that we know. Fg is mg. Fa is ma. Fk for springs minus kx. N is a normal force, is minus mg because it's upwards. And then for friction, we have static friction minus mu s times n, that same n. And for the kinetic friction, we have minus mu k n. Wow. Let's draw a quick diagram and kind of put them all together. Say we have a box here. The box itself is resting on a table. Could be a wheel cart or anything. Imagine I'm pulling it this way with a rope or a tension. So there's a F. I'm going to call it FA. So I'm pulling it, but it has friction, which pulls it backward. So we can say that this is maybe moving or not moving, I don't mind. Same drawing. FK for friction, it's opposite side. Then there's also the force of gravity, Fg, which is applied on the y-axis, the negative y-axis. And it's also being pushed back by the Earth with a normal force, Fn. So this is a system of forces. They all have their little formulas, which are right here. And we can calculate the final force vector, right? So Fg and Fn are going to cancel out because the object is not skipping up or down, right? The object is not doing this. The object keeps going on the x-axis, not an object that's skipping. Why is it not skipping? Because if you remove me from the equation, like this, what do we have now? We have a mass, which is attracted by the Earth, pushed back by the Earth, which is these two, and there's a force of friction that does not really exist right now because I'm not pulling it, right? So the object is not jumping around. It's just an object resting. So when I start pulling, there's a friction force that goes against my pull. It'll be a little different when I start pulling this way. If I give it a go this way, then it might be above Fg. If it's above Fg, right, if it's more than this, then the object might start skipping, right? It might start doing this when I pull like that. But if I pull straight, if I just give it a go this way, it's going to increase the friction. We're going to hear more sound by the friction, but we will not see the object skip up like this in its movement. If it doesn't do that in its movement on the y-axis, if it doesn't move on the y-axis, then there is no y acceleration. Right? There's going to be an x acceleration, which could be 3 or 4, so on, but there's no y acceleration. And that's really important, and we'll come back to that when we resolve the equations. Okay. Example 1. Snowboarder has lunch at an all-you-can-eat buffet. As a result, his mass increases by 8.5 kilogram. Calculate the increase in the kinetic force of friction. Fk is what? Between his snowboard and wet snow on a flat surface. Oh, you want me to take from the previous screen? Sure. Up. Here. And you... No. I think I like to merge. Okay, so let's put this here. These are mu, coefficient of kinetic friction. This is mu. Okay. Mu is a U with a little bar in the front instead of the back. The Greek letter. So we're basically saying snowboard on dry snow or wet snow. So basically, we're starting to get a lot of formulas now, and you might be a little confused as to where to start. So let's review how we work in physics. We read the paragraph, take the information that we have, all you can eat Buffett, his mass increase, so we put the mass, calculate the increase in kinetic force of friction. So this is the question. That's it. So basically, what you could start with here is you've written that down. Now what? We don't know what we're missing. We don't know what to do. All you need to do is take a step in the right direction. We're looking for Fk. So let's write down the formula for Fk. Can I work better? Can I please work better? This. So Fk will be mu k n. Oh, okay, not bad. Okay, so in order to find Fk, I need mu k and n. Okay, what's mu k? So mu k is the coefficient of friction between what? Between his snowboard and wet snow. Snowboard and wet snow. 0.1. Good, so I need that. So I'm going to put that here, because who knew what mu k was? 0.1. No units, you'll notice. It's a coefficient. Okay, so I'm almost ready. I've got mu k. Now I need n. What do I do with n? What is n? I can't see n. We're going to go get our formula for n. And we're going to find n. So n is the opposite of Fg, right? The gravity. This is the snow pushing back. So n is minus Fg. In this case, minus mg, which is minus m is 8.5, g is minus 9.8. I'm not writing that here. Okay, so the minus and the minus cancel out. And you get 8.5 times 9.8. is 83.3. 83.3 what? So N is Fg, but the opposite. So what's the units for Fg? The same units for N. So these are newtons. And you'll notice that it's positive because it's up, right? The normal force is up. Now what do we do with that normal force? We put it here inside this formula. So we go back to our formula for Fk and write mu k, normal mu, small k, big N. And so Fk is equal to 0.1 times that force, normal force that we found. Is there a minus? Yeah, there's a minus. Look. Minus. Because it's always on the opposite. It's always against the movement. 8.33 Newton. They're all forces. It's always newtons. Right? See this Newton right here? So this would be the new or the added force of friction because the guy ate a meal. Right? So you see it here, 8 newtons. Where did his minus go? Because they introduced it with minuses, no? More examples. Let's do another one. Example 2. How much applied force, Fa, that's the question, is needed to keep a 62 kilogram mass moving across a floor at constant speed, the acceleration is 0, if the coefficient of friction and it's going to be a kinetic friction is 0.18. So again, we're moving it, it's going well. Now I want to try to slow down, but push enough so that it doesn't stop. Keep pushing as much, as little as I can, but it doesn't stop because the kinetic friction allows it. And until I push so little that the kinetic friction says enough. And they say, remember, the applied force must be equal to the kinetic frictional force to keep the crate moving. So we'll just write that down since they spell it out for us. What did they say? The applied force must equal the kinetic frictional force. Like this. And I put them in reverse because I'm going to put the minus in the right spots. And we can understand the situation if we make a little drawing. We have an object, there is an applied force, like I'm here, and I'm pushing it, but it's going that way. But there's also a force of friction. So there's Fa, which is a positive Fa, and there's Fk, which is a negative Fk. And if you talk about the forces, this force is equal to this force, but it's the negative of this force. Like FA is the negative of this, in order to transform this into this. Changes the direction. So that's why I wrote negative. That's the current situation. On top of that, we have N, because every time we talk about Fk, it's mu Kn. So we need to have N in our drawing. If we have an N, it's because there's an Fg pulling the object down. And here, you also can recognize that N is going to be equal to minus Fg. Because however much this book weighs on the table will return an opposite force equal. Why equal? Because the object is not moving. If the object would start to move, then he would have an acceleration which not be zero. The object starts moving, he's accelerating. The book is not accelerating up or down, right? F equals ma. If the acceleration is zero, because it's not accelerating up or down, then the force has to be zero, or the sum of the force has to be zero. And this is what's going on. So if the sum of the force is zero, then N is equal to Fg. Let's put this right here. I'm trying to build something nice for you, okay? You tried drawing with paint? Okay, so recognize that this is the X part of the system. This is the Y part of the system. Let me, I'm so nice. I'm so nice trying to do this right. Such a good man. There you go. So you can see how this is the X part of the system. This is the Y part of the system. And we've talked about how in Y, the object is not skipping up or going down. So the acceleration is zero. We'll call this a Y because it's the Y acceleration that's zero. In our case here, normally the acceleration in X is not zero. It could be 3 because we push the box enough to accelerate it. But in this case, the acceleration is 0 because they made it so that we are at the very edge of what the friction allows us to go. So we're lowering our forces low in order to match the kinetic force to be as low as possible until the object stops because of the static force. What do we want? How much applied force? So basically we set it here. Okay, so this is a regular situation. This is also a regular situation. This is very regular. This is not regular. This is our problem. And in this case, if this is our problem, we're going to bring that here. Okay, so this is normal. And this is normal. But our problem says this. So basically, they told us that the force of the Fa is equal to minus Fk. There is a line before that I'd like to introduce. The sum of the forces in X are equal to what? So what are all the forces in the X-axis? We have F A and we have F A. Right? There's FA and there's FK. No matter how positive or negative they are, if you add those together, if this is a positive force and this is a negative force, you add them together, the result will be 0. Right? If they're equal. And when you get the forces together, you end up with a resulting force. Right? We used to do that. Remember? A resulting force. Right? So a resulting force is add this one to this one, and you end up with this resulting force. Or add this one, and your resulting force is this. Right? Same here. But if it's the resulting force, it is also the resulting acceleration. MA, right? If this is FR as a result, then this is MAR. We'll call it AX because the total of the forces in X will create an acceleration for the mobile in X. In this case, AX is 0. If AX is 0, then we're going to take this part here and write that FA plus FK is equal to M times 0. Then M times 0 is 0, and you get FA plus Fk equals 0. And if you move the plus Fk on the other side, you end up with this here, right? But this is where it comes from. Except I want you to get this idea here. This is the toolbox. Okay, let's continue. So what happens? What have I done? So we've taken some information. We've seen the system. We drew the system. We then ask, what is the sum of the forces in X? We added them up. There's all these forces that we just add them up as we sum up, and then we make it equal to MAX, which will be the resulting acceleration, which we normally care about. If we want to accelerate it. And it told us that the acceleration was 0. From then we took the forces, we summed them up, it should be 0. Right? If you sum up those two forces, it doesn't move. Or there's no acceleration. Because it's a constant speed. And from there, we derived this formula. This formula is telling us the current situation. This is the current situation. Every time you have a different problem, it will be a different situation. But with this is true. This is the current situation. The force that we apply is equal exactly to the opposite force of friction. And since we want to know Fa, we simply need to decouple this, find Fk, which is equal to mu kn. Do we have mu k? Yeah, we do have mu k right here. Do we have n? No. We can find n. So n, in our case, is always equal to the opposite of Fg. Where does this idea come from? Does it come from the same idea that we've seen here? Absolutely. In fact, let's dive in. So again, another example. The sum. This time we're going to do the sum of the forces in Y. So what are the forces in Y? There's N, right? What are the forces in Y? There's right here. There's N and Fg. So N plus Fg. Now, the forces would create an acceleration, a y acceleration. What is the y acceleration? AKA, by how much is the object accelerating upwards or downwards? 0. Right? The object is not skipping, moving, going up or down. If this is 0, then this is 0. All right, if, or even when, I think when is even better. When AY is 0, you get this. And from here, if you move the Fg on the other side, you get minus Fg. Notice how these two things are the same. When. You see? See how this box and this box are the same? So it comes from these ideas. I want you to see it now because this tool is what helped me understand the situation. Okay. So what we're doing is we're kind of moving on to, so we need to find n. N is a y value. We're gonna going to this side and we're figuring out some y values. N is equal to minus Fg, which is minus mg, which is minus 68 kilogram. I'm not writing kilograms. Times minus 9.8 meter per second square for the gravity. We could have written all that up there. So the normal force will be a positive force, very important. Be a positive force. 68 times 9.8. Six point 4 Newton. So we go back on this side, we plug that in there, and we get Fa is equal to minus, what's mu k again? 0.18, 0.18 times 666.4. And the FA is hold up. So this minus has nothing to do with the fact that this equation has a minus in it, right? Mu kn. So you can see how I made a mistake here, because FA is minus FK, which would be minus mu kn. The two minus annihilates and make an FA that's positive. So FA will be this. That put that here, we'll write a note. The minus. This is the minus here, and this is the minus there. And they make a plus, and this one goes away. Like that. You're left with the answer. 0.18 times 666.4. 119.95 newtons. So 120 newtons. Good. We got the right solution. 1.1 times 10 to the 2. 1, 2. So they've cut off the 9, which is not a good idea. And maybe they did with another number that I'm not familiar with. And you'll notice how everything is often on a flat surface. As I said earlier, this is the first half of the chapter. Everything's on a flat surface. And at some point we'll do an incline, and there'll be a few more angles to worry about. I can't believe we're not done this chapter by now. Are we not done? Yeah. So, self-assessment. This is not the quiz, right? Is the following statement true or false? I kid you not, I've never done this. Just go with the note that we took. Okay? Is the following statement true or false? Weight is the gravitational force exerted on an object and is measured in kilograms. False. Not kilograms. Newtons. It's a force. Weight is a force in newtons. A man is pulling a crate across the floor using a rope. What type of force is the sideways force that the rope exerts on the crate? I would call a tension. Normal is up, frictional is back, gravitational is down, so it's tension. How does a pulley affect the tension force of a rope? It does not change the strength of it, it changes the direction of it without changing its magnitude. Is the following statement true or false? Normal force always acts in the direction opposite to the object's weight. I think so. I think you have no choice. Uh-oh. normal force always acts in the direction opposite to the weight. What does he say? Incorrect. When an object is in contact with the surface exerts a force on the object that is perpendicular to the surface. When an object is on an incline, okay, talking about this here. When the object is on an incline, normal force does not act in the direction opposite to the weight. Right? You can see how here the weight is clearly down, but the normal force is not opposed to the weight, but opposed to the surface. So the normal force is always opposed to the surface. Did I write that down? Perpendicular to the surface. So what do we do with that? Underscore. That's right. Which of the following options are correct statements about both kinetic and static? Select all that apply. They both require the same amount of applied force in order to overcome. That's wrong. They both oppose the motion. Yes. They both act in a direction parallel to the surface of the object in contact. I think so. You can't really have a force, a friction force like this or like that. It's unheard of. The magnitude of a frictional force, so how much, depends on the type of surface. I don't think so. We're gonna click it and it says wrong, and that has to do with, and this one is wrong too. Yeah, and this last part has to do with dependent on what, right? And that's not one of them. You and a friend need to push a piano to the other side of the room. What type of force is occurring between the piano and the floor that makes it difficult for you to try to get the piano to move from rest? Well, if it's moving from rest, it's always static friction. That's what makes it difficult. A boy pulls a block of wood. Oh, we have a real problem. A boy pulls a block of wood. M equal unknown. We'll just write M. Across a rough surface at a constant velocity. Nice. So constant velocity tells us that the AX is 0. Okay? That's the constant velocity V. So M, V, they don't change. A equals 0, or AX. AY is already 0. We don't know that yet, but most of the time AY is 0, unless it's moving up or down. He's pulling it. He's pulling it with a tension, and there is a force of friction. Too small, Charles. Okay. I would call this FA because he's applying the force, which is equal to the tension, which is equal to 20 Newton. Positive. The coefficient of kinetic friction, that's mu K, kinetic friction, is 0.3. What is the force of friction? Fk. Unknown. All right. So a lot of things here. We just start with our first step. Fk is what we're looking for. There's only one formula, which is minus mu kn. We need n. So n is here. And it's the opposite of Fg here. So n, again, because of this, then our spiel from above is, so this is basically saying that n will be minus Fg, and this part will also state that the tension will be minus Fk. Right? These are extremely important details because they give us the structure of our force system. So you can use this. If you don't have an acceleration in x, you can use this. If you don't have an acceleration in y, then there's no other forces, right? But if more people are starting to pull on the block, or if more people are sitting down on the block, then this will change, because there will be more forces in action. So n will be minus Fg. So minus Fg is minus, no, Fg is equal to mg. And then your block, what? Don't tell me this is the answer. I don't want to hear about it. What is the force of friction? Don't tell me that. I can find what the mass is. We don't have the mass. But we can find what the mass is. Can we not? We can. It's just a very complex problem. Fg is mg. I don't have Fg. I have g. I bet you that's the answer, and I can still do it. No, okay. It's not. Okay. Why would it be so difficult? Let's start with this part here. So we know what g is. We don't know what Fg is. But Fg is minus n. And what is n again? You want me to write them down as I go about this? What a weird problem. What a weird problem. That's a fine problem in physics. It's just hard. It's just like, okay, here's a really epic problem in physics. Go ahead, do it. Alone. So Fg is mg. And then I write that n is minus Fg. So I write this. And then we write that n is minus mu k. No. Where do we use n again? Fk is mu kn. Right? So in this part, n was this. So in other words, Fg was minus n. I'm not even sure if this is the right way, like the intended way. I'm just cheesing everything. And then here, I don't like, so again, I know what G is. I don't know what M is. And I don't know what N is. So I'm going to change N here. I want to keep M because it's going to go away at some point. I'm going to change N. So N would be equal to Fk over mu k. I'm going to do that here. Minus Fk over mu k is equal to mg. Great. Fk. What about Fk? Do we want Fk to be equal to the tension? Yes. Yes, yes. Because there is no acceleration, there is a tension, so the Fk is equal to the tension. So the tension is equal to minus Fk, or Fk is equal to minus the tension. So minus tension is over mu k is equal to mg. Right. I'm not sure this is going to be working. And then the tension is 20 Newton. This goes away. Here comes the edit. Mu k we have. Great, so I can find the mass. Such a baller. I did what I set out to do. I found the mass. Isn't that what I want to do? Point 0.3. Yeah, so I can totally find the mass. Great. Ah, there's a minus. What the heck? So if I divide 20 by 0.3 times 9.8, I have the mass. I'll write it down. This is a blooper. It's already a blooper. So 0.3 times 9.8. It's all true, but it's just, I don't need to, it's not the intended way for sure. This is 294. 20 divided by 294. Wow. M is equal to 6.8 kilogram. Okay, let's come back to that. Let's take all of this and move it somewhere else. All of this is true and it should work out. I'll verify the answer at the end. Let's try again. So what do we want to find? Fk? Fk is equal to what? Just want to make sure that's the question. Yeah. The kinetic friction. So Fk is equal to mu k n. Okay, let's start here. So starting with the first step. Do we have n? No. But n is minus mg. Okay. Mu k we like mu k, that's good. I'm not editing this video. You need to figure out that it's hard sometimes. So mu k is good. We like that. N is not good. We want to replace that with Fg or Mg. Okay. So we either want this or, and we can also make this. Right? So either of these, and I can actually put this under here, is just a follow-up of this. So we don't have the mass. No, we don't. Wait up. We also have this guy here. The tension, that makes more sense for a problem like this. So the tension, which is 20, is, because there is no acceleration, then T, I'm actually using this to solve this. So T and Fk are the same because A is 0. Right. So the right way to start this would have been to say that since AX is equal 0, or there is no acceleration as there is tension with this diagram, then the tension and the kinetic friction are equal. Wow, so eloquent. And if this is minus 20, all I'm doing is changing everything from its side, then we can say that not Fx, Fk, then Fk would be minus 20 Newton oh, slow down. Fk, okay. And so this is the right answer. It says here that's right, and they're equal. I'm having a lot of fun trying to figure out what the mass is, so I think the rest of the video will be about that. Oh, I haven't clicked done, whatever. So you're good to do the challenge then? I'm just going to continue this idea here, because all of this is true. Fk is mu kn. Is it minus mu kn? Yes. And then Fk, so n is also minus. So I'm just going to make sure my minus business is good. You don't want to put the minus, I don't mind as much. Just make sure your answer makes sense. You don't want to have a minus 45 kilogram answers, or if your answer is in minus when it should be in plus, that's also going to be a mistake. So do whatever you want with the minus at this stage. But if you keep them, it makes sense. We figured out that, okay, so let's say I start here. Fk is this, Fk is this, Fk is this. Fk is also minus the tension, is equal to mu k mg. And the tension is also 20. I don't need that. I know the tension, am I not? But which one do I not know? I know this, and I believe I know this. Yes, we do. Actually, these are the only things we have. Mu k, t, and naturally g. So since I know all of these, I can find the mass. By rearranging, we would get that the mass is minus t divided by mu k g. Right? If you divide both sides by mu k and g, you end up with this. And we get minus 20 over 0.3 times, we're back here, times minus 9.8. Right, so the problem here was that minus tension, 6.8 kilograms. Notice how the minus cancel out. Minus problem here, minus Fk, N is, this is true, but this is not true. From here to here, N is minus Fk. No. Whoa. N is minus Fg. Ah, there it is. I see it. Right here, we are missing the minus. I'm going to take all of that, get rid of it, because this is finding the mass. Extra, we'll call it extra. Finding mass. Extra. Finding M. Cool. I hope this was helpful. Thank you for your time today. And again, I'm available all the time. See ya.